Unfortunately, we don't stop irrigating. So there's a lot that goes into this. So as I said, we're measuring for uniformity, distribution or emission uniformity. Those two words are kind of used back and forth interchangeably. Primarily when we're talking about micro irrigation systems, we are primarily talking about emission uniformity, a measurement of the water that is applied. Distribution uniformity can also mean that same thing, a measurement of water applied, that also takes some time to look at the infiltration across a field, things like that. So we measure in sections. We usually take about 20 water flow measurements in an irrigation block to determine what flow, average flow, and also, so the two numbers that we're looking for when we're measuring is we're looking for the average overall of flow, and then we are comparing that to the lowest performing quarter or 25%. And you take that 25% average number and you divide the overall average into it to arrive at a percentage representation of uniformity. And we'll explain how that's used later when we get into irrigation scheduling. We then take pressure readings around the block as well. We normally take 8 irrigation or pressure readings at risers throughout the field, not just where water comes into the line, but just up and down the lines. So like you might take a pressure reading at the end of the line, close to the inlet, somewhere in the middle, just kind of work your way around. There's no, they used to recommend a very patterned way of taking these readings, and then somebody did a study between the viability of the data between that very regimented measurement system and doing what they called the drunkard stagger. Just imagine someone who's under the influence walking down a not straight line through the grove, and that the data between both methods of collection is statistically the same. And so the drunkard stagger is basically just makes it easier because you don't really have to remember where you've been or where you were. You just take measurements and record them as you go. All of this was developed at the San Luis Obispo at their Irrigation Research Technology Center. And they primarily developed the way of doing an irrigation system evaluation for farms in the Central Valley here in California. And they, in that system, the way that they do things, they take more pressure readings than they do flow readings. Most of what they're working on are drip systems and large fields, 40, 60, 80, 100 acres at a go. Whereas, you know, here, San Diego County, according to the statistics, the average size of a farm in San Diego is 9 acres, but that's also including the rangeland in the backcountry. And our median size is 4 acres. If you were to look at our irrigated acreage in the county, you would find that that median number of 4 is probably the average size farm in San Diego for irrigated lands. So what we're learning from this, as I said, is we're a measurement of uniformity. How evenly is water spread across a field? And in the ratings, any uniformity below 59% is unacceptable. Anything in this is poor. Anything in the 70s is fair. Anything in the 80s is considered good, and anything above 90 is considered excellent. Industry standard for a well-maintained micro irrigation sprinkler system, say in an avocado or citrus grove, would be 85%. That's the number we're shooting for. with a micro sprinkler. In drip, we consider standard at 90%. So how can an irrigation system evaluation save money? So low uniformity means water wasted. If this field is, if you think about that soil profile, irrigation event's job is to fill that soil profile. And this is an example of a poorly uniform system. You can see the lower part of the field is quite full. The upper part of the field is not full, not as full. And so if we're going to get those trees at the upper part of the field full, we're going to have to greatly overwater the lower part of the grove. Let's see. So here it is in terms of looking at the numbers. An irrigation set has an average flow of 20 gallons per hour. The system uniformity is 85%, and the set has 100 plants that need 150 gallons of water to meet the evapotranspiration. So evapotranspiration, C stands for crop. Evapotranspiration is a measurement of how much water has moved through the plants primarily. That's the T. The transpiration, evaporation is just water that is evaporated off the surface of the soil back into the atmosphere. With a micro irrigation system, the typical evaporation rate is only 1%. So most of the water has moved through the system, through the plants themselves. And the calculation for evapotranspiration is calculated here in California with the California Irrigation Management Information System. It's a series of weather stations throughout the state coupled with satellite imagery. And the reason that we're able to utilize the satellites, and they use the GOES global spatial system, passes around the earth on once every 24 hours. So it gives us a daily reading. But the reason that we're able to rely on that is because the algorithm that calculates evapotranspiration is 80% of the algorithm is the solar radiation. Temperature, wind, those are factors. Humidity also a factor in the calculation. They get those from the area of weather stations, but the big component of the calculation is solar radiation, how much sun is hitting the ground. So the run for the average for this situation would be 7.5 hours when you have that industry standard uniformity of 85%. So the locator average flow is 17 gallons per hour, and so the additional run time is 1.3 hours. I don't know what that. So, resulting in 1,900 gallons applied. So that would be the situation where you have a pretty uniform system, industry standard. You've got 20 gallon per hour sprinklers. You need to apply 150 gallons of water. But so we change our situation. Instead of a uniformity of 85, we have a uniformity of 70%. Same 100 plants need 150 gallons of water to meet ETC. So the run, 7.5 hours, low quarter flow is 14 gallon per hour. The additional run time is 3.2 hours. So we were at 1.3. So we need to, instead of applying 1,950 gallons of water, it's 4,800 extra gallons of water. So we've greatly increased how much water we've got to apply to the field when our uniformity is only 70%. Now the average based on 12 years of doing irrigation system evaluations in San Diego County that I've seen, the average uniformity is 74%. So 70 is a little bit below what we normally find in a field, but still both of them, 74 wouldn't be greatly improved, maybe 4,000 or 3,900 instead of 4,800. So if we look at it in terms of water applied and the beneficial use of water, in ag, we're applying water for economic benefit to grow plants, to produce crops, to produce food for people, food, medicine, fiber, but primarily food. So when we have a low uniformity, and this is really a bad situation. So we have a uniformity here of 49%. The beneficial water applied, this is measured in inches rather than gallons. We could do the math if you really want me to figure out how many gallons this is, but it's just under 2 inches of beneficial water applied, and the total water applied was 4.5 inches. Question, when you say 7.5 hours, is that in just one watering session or over a day, week, month? So that's saying that to meet that ETC what was required was 7.5 hours. The way that example was looking at it was more or less a single irrigation event, but it is possible that you could split that into 2 irrigation events, say a 2, 3.5, or a 3.5 and a 4-hour irrigation event during the week, whatever best works for your system, your availability of time, labor, those kinds of things. But now here's the same example of beneficial water applied. If we get our uniformity way above standard to 92%, which I've seen plenty of systems once you have properly installed pressure regulators and pressure compensating sprinklers, we can see uniformity. We still have the 4.5 inches applied water with the average infiltration rate. This is still at 4 inches. Official water is above 3.5 inches. So we've gained 1.5 inches of beneficial water applied. And the reason we're able to say that is because water is more evenly spread. So we're delivering it basically to the root zone at the same time, as opposed to water coming in at one end of the field more than is needed and draining out the bottom of the field. In our say draining out the bottom, we mean underground bottom. In other settings and other situations, oftentimes when they talk about the bottom of the field, they're talking about the end of a row, say the end of a furrow in flood irrigation, the end of a furrow where the water is coming out into an overflow system. But in our situation, because of our shallow soils and bedrock at 18 to 24 inches in many instances, draining out the bottom means that it's going down, hitting that solid surface below the roots and sliding down the hill. So if we look at some of the recommendations made after an irrigation evaluation, oftentimes in older systems that don't have pressure regulators. Pressure regulators are installed in each row, typically. You can put a big regulator at the top, at the beginning of a system, if pressure is really high. Sometimes that's needed. Here where I am, our pressure at the meter is 300 pounds. So we have a pressure regulator right at the beginning of the field to bring pressure down to about 100 PSI, and then regulators throughout the field. So this is an example here in this picture of sub-main, going from that flex hose underground to a PVC line that runs along the row of trees. And there's no pressure regulator in the system. Ideally, though, we would want to see this device, the pressure regulator, between the hose bib and the hose, is where you would place that 20 psi. Is typically what we use, and the primary reason that we use 20 psi is that most of our sprinklers, when you see, if you go to an irrigation store and you see a flow rate on a label on the shelf, that flow rate is based upon 20 psi. So that's what the sprinkler set, that's its factory standard flow. And so that's what we want to try as best we can to get the pressure to 20 psi in the field. These devices are about $10 a piece, and typically one is put in each of these lateral inlets. Also, uniform sprinkler types. There's no industry standard to the coloring that is put onto sprinkler nozzles. One manufacturer's red might be 24 gallons per hour, and another manufacturer's red sprinkler is 65 gallons per hour. So color doesn't mean anything if you accidentally pick up the wrong brand compared to what you have in the rest of the field. It's not uncommon for us to find a lot of different sprinklers in the field when doing an irrigation system evaluation. Some of that is because certain sprinklers that were popular in, say, 20 years ago are no longer manufactured. So people are just trying to find something close in flow. And so they're putting other brands out into the grove simply because that's what's currently available when they go to the store. And sometimes it's people are trying to match different tree sizes. And so they have a mix, say on the shelf at the farm, and an irrigator might grab a handful and not really pay attention to what is being replaced, because sprinklers do become damaged. Oftentimes, coyotes chew on them or they get plugged for whatever reason. And so in replacing sprinklers, if we don't have a set sprinkler, the only one on the farm, or maybe two if we've got different size trees or something, but as much as possible, we need to limit how many types of sprinklers are available for an irrigator to go out and make a change in the field. Because that's the primary reason why we find different sprinklers in the field, is because an irrigator has made a change from what they found available. These are a couple different brands here. As I said, each of these colors is a different flow. So these top two are Toro brands. The blue one's 33 gallons per hour, the red 65. This yellow is a Challenger sprinkler, and it's yellow, and it's, I believe, is 40 gallons per hour. So all three of these are really higher flow sprinklers than what most soils in our area would want, because the infiltration rate that we have tend to be relatively low, meaning that it takes a while for the water to infiltrate. And so when you're applying this level of water, you can get some actual surface runoff. Just an example of a sprinkler. Sometimes our main and sub-main layouts don't match. The worst case I ever saw was a 9-acre grove, had a 2-inch meter. The pipe started 2 inches at the bottom. It was a fairly steep grove, probably a 25% slope. By the time we got to the top of the grove, the pipe had been reduced all the way down to 1 inch. And they had 9 irrigation blocks. We redesigned the system. We put in a 3-inch main from the meter all the way to the top of the hill. Then installed the laterals coming back down, and off of that 3-inch with 1-inch laterals, and we got from 9 irrigation blocks, we ended up with 3. So we need to make sure that we maintain as big a pipe going up a hill as we can. While it can be more expensive to put in, say, a 3-inch line than a 2-inch line, the difference in friction loss between a 2-inch pipe and a 3-inch pipe in PVC is 4 times. So there's 4 times more friction in a 2-inch line than there is in a 3-inch line. And so if you had a 3-inch line, you'd virtually have zero friction loss. And what that means is if you had 65 pounds of pressure at the bottom of the hill at the meter, assuming your meter, obviously sometimes they're at the top, but for our example, we'll say the meter's at the bottom of the hill, and you're running 300 feet of 3-inch pipe, and friction loss or pressure loss is measured in 100 per 100-foot section of pipe. So we'd have 3 sections. If we were 65 pounds at the bottom, I would expect in a 3-inch line to find 60 pounds at the top. We would only lose 5 pounds of pressure. Whereas if it was a 2-inch line, we would lose 20 pounds of pressure. So if we were 65 at the bottom, we'd be 45 at the top. 45 would still be sufficient. It would work, but it wouldn't be as efficient as a 3-inch line. We also, do work with drip irrigation as well. In our area, we find, vineyards are on drip. Most of the cut flower, the perennial cut flowers like Australian wax, Protea, all the eucalyptus, the different stem materials, leucadendrons are on drip irrigation. And some of the newer crops like dragon fruit, passion fruit, those usually tend to be on drip as well. Irrigation scheduling. So we have weather-based irrigation scheduling. This is a picture of the Simis weather station that's in the Sample Squall Valley. It's out on the east end of the valley. What has become was a pasture is now an alfalfa field, but the underneath the weather station is pasture grass. Is a system of weather stations throughout the state of California. We have several different stations here in San Diego, as well as 2 in Temecula. The one in Temecula, Station 62, is if you were, say, in Fallbrook or Rainbow, you probably would be better served in some ways you'd be best served probably to look at that weather station 62, and do a comparison then also with weather station 153, which is this one in the picture out in Sample Squall Valley. And you would, because sometimes because of where this 62 is, it doesn't have as much coastal influence as you might experience in some places in Fallbrook. So if you were going to use weather-based and that was where you were located, I would recommend you pull the data from both and do comparisons. And we've got some spreadsheets available to people that we can send if you'll leave your contact information, and they can help you make those comparisons. As I said, there's also the spatial data. So the spatial data, that system, when you go into the Simis web, and if you just Google California Irrigation Management Information System, you can find their website. And the spatial data, you can actually put in your address and get an email every day or weekly, however you want to receive it, of the evapotranspiration number from your actual property. There's also soil moisture sensors. So we have tensiometers. This graphic here shows basically what a tensiometer looks like in the soil. The upper picture are actual tensiometers that have been installed in the ground. Tensiometers can be just manual analog read devices. You see this gauge here. It's a pressure gauge. This basically acts like a root in the soil. You fill this tube with water. It has a clay tip in which water can move in both directions, in and out. And the gauge, then you pull a vacuum to the top of the chamber, and this tube then works like a root. It's measuring how much energy is needed for a root to pull water from the soil. Um, and then as soil dries out, greater energy is needed, so the pressure in the gauge goes up because the vacuum becomes stronger to try and pull water. When the soil is saturated, the gauge goes down to zero because little energy is needed for water to move back and forth across the clay tip. The device on the right here at the bottom is a watermark, also made by the same company here as the top, aerometer. The watermarks are a block of a matrix. It's made up of, it used to just be made of gypsum, but they now make them of a composite material because gypsum breaks down too quickly. So this is a porous material. Water can move through past that metal screen and across the block. There's a wire inside. A signal is going through that wire about every 15 minutes. And it's then measuring resistance, but they've translated that resistance measurement into the same kind of number that you would measure in a tensiometer. So both of these are measuring tension, how much energy. We then have probes at current strength, and that is based upon what is available, or how easily water moves, or how easily electricity moves through the soil based upon the soil's level of saturation. Oops, and not ready for that yet, sorry. And so the capacitance probes measure volume. What's the volume of water available in the soil? So tensiometers, like I said, act like a root. How to use them in making irrigation decisions typically takes about 3 weeks, not very long. But a capacitance probe, while it provides great information, the learning curve is a little longer. It could be 8 to 10 weeks before you fully understand what that percentage number means. That doesn't mean that the data is anything wrong with the data. It just means more time is needed to make good irrigation decisions. I would never put one of these devices in the soil, either type, and immediately begin to change how I was irrigating. If I was irrigating based on weather data and applying how much water the weather data said had left the soil, I would continue that practice using the soil moisture sensor information to see how we're doing in comparison to the weather data, and then begin to make adjustments after probably 6 to 8 weeks of irrigating. There's also the good old moisture feel method. This is a flyer that's produced by USDA, and it shows what different soil types appear to be when they're down to 25 to 50% available water. Got to have the soil probe itself to be able to pull the soil core to do the hand method. Any questions? Okay. The question, how good are aerometers? A properly maintained tensiometer is a very good device. They're good. They last for 10 or 15 years. They're now set up so that they can be connected to an electric data logger, so you don't have to go out and read them manually on a regular basis. And maintaining the water in the tube is pretty easy. You check it maybe every 3 weeks, and just make sure there's enough in there. And if you're irrigating properly, there usually is no need to service the device. The problem happens is when you let it go too long between irrigations and soil gets too dry, the tensiometer, the aerometer device loses contact with the soil. And so if it loses contact with the soil, you've got to pull it out, re-wet the soil, and reinstall it in the ground. So as long as proper soil moisture is maintained, the device works great. But that's usually the problem isn't with the device, it's with an irrigator letting soil dry out too much. And so contact is lost, and so you have to reestablish the device. So we do have financial, oops, did I hide everything? Oops, sorry. Well, I forgot to complete a slide. I apologize. So there is financial money available. Okay, so we're back up and we're going to answer Dave's question. So we have baby trees, 5 to 10 years. We have 10 to 20-year-old trees. You indicated one size micro sprinkler, maybe two would be sufficient. I want to confirm I have 3 different types of sprinklers. Okay, so if these trees are in this mixed irrigation block, correct? You don't just have small trees in one irrigation block and big trees in another. You've got small trees interplanted. Yes, mixed. Okay. So then we're trying to do the best we can to determine how to best apply water based upon the diameter of trees. We do have a chart that we can share with you that was developed by University of California that shows water requirement for avocados based on that tree diameter. And when we're doing, like, if you've got 3 different types of sprinklers, the recommendation I would make is that you use flow rates that are divisible. As an example, that you have, so Toro makes their pressure compensating sprinklers in a 9, an 18, and a 33, or you could do 9, 18, 24. So especially the 9 and 18 work really well because you can put a 9-gallon on a small tree and an 18-gallon on a big tree, and so you're delivering half the amount of water to the small tree that you're delivering to the large tree. When you're getting to the further along the scale there, you're getting, it's a little bit more challenging. If you've got a 33-gallon sprinkler, that might work. 24 would work as well. Just depends on how close in size the trees are. Like I said, that the diameter chart would be helpful. I'm pretty sure we've got your contact information, so we can get that to you. But that's my recommendation. If you've got mixed size trees in a block, you want to use sprinklers, but flow rates are divisible by each other. So that's why I always start with the 9 and 18. And then if we need to have something a little bit more, either go to the 24 or 33, depending upon how big the big trees are. Is that helpful? All right. So the slide here that's showing is saying USDA. So we'll talk about USDA programs in a minute. But right now, the program that we're most concerned about, if you are still in a water district that is part of the water authority, is the Agricultural Irrigation Efficiency. This is through a grant from Department of Water Resources. That money comes down to the water authority, and then they distribute it. The current program has offers a financial rebate of $1,000 per acre for irrigation materials. Correct, Lisa? Just irrigation materials, right? No labor. Yeah, I'm pretty sure it's just for irrigation materials. Yeah, got the word. That is correct. Yeah, so it doesn't pay for labor, but it does pay for system components, valves, pipe, sprinklers, um, hose, drip emitters, whatever it is you have. Yes, Fallbrook is out of that program now. Both Fallbrook and Rainbow have fully detached from Water Authority. So the programs that are available to those growers are the USDA program, which we can talk about offline. But the USDA program's funding is very similar to what's available from the Water Authority. So if you are interested in the financial incentives through the Water Authority, the place to start is the irrigation system evaluation. Whether you are in, you don't need to worry about which resource conservation district you are in. Because the point of contact to get the ball rolling is Mission Resource Conservation District, and I will type the his phone number is 760-728-1332. So that's the phone number for Mission. That's who you would call to get things started. They would schedule the irrigation evaluation either with staff from Mission or staff from Greater San Diego, whichever. To get things started for the AIEP program. Yes, David, the 2022 evaluation done by MRCD, NRCS will work with that for sure. And any other questions, comments? Yeah, in your irrigation evaluation report, you would receive a list of recommended materials needed to make the improvements to bring about that higher uniformity that we talked about, and an estimate of cost based on information that we've gathered from different irrigation suppliers around the area. It's not a set estimate, but it's just a kind of an average of costs based on different suppliers around. Right. Anything else? Any other questions? The NRCS office phone number is 760-745-2061. And David, if you call them, tell them you're interested in the RCPP program application. That's Conservation Partnership, which FPUD is part of. Anything else? Any other questions, comments? I'm typing it up, Dave.